record. Yes. So how do I get rid of that one? Yes. In this the Dropbox area shared files, there are lectures, and I think F3, it should be present also in the box area. We will try to keep similar content in box and Dropbox area. So those of you that have access to box don't need anything more, and those of you with access to Dropbox should be able to see that also. So how do you scattering is one can look at the phenomenon of scattering in several ways, either a phenomenological description of what happens, which is a bit difficult because then we start to speak about photons impinging on charge density around the atoms, and then exciting the atoms, and when the atoms relax, radiation is sent out in all directions in principle. Every atom acts as a spherical scatterer, and then since there are if it would be only one atom, then we can put it in the origin, and then we have get rid of a lot of different problems. But only one atom in vacuum is perhaps not an interesting subject to study, even though there are people who do that, physicists mainly. But if there are several atoms in a crystal, the emitted radiation from each of the atoms will sort of interfere with each other. Well, how to speak about light that is scattered. And there are in principle 3 different models of light. You can have a light ray, for example, an arrow. Well, traditional art and lightning at theaters and such things, then light rays is a useful concept. And we speak about light rays also, even though no one has seen the rays, but we sense the light anyway. One can see light as a bunch of particles arriving along some path. Maybe the path could be described as the light ray. These particles we call photons. Or we model light by a wave phenomenon. The problem with understanding what light is, in my opinion, tremendous, but you don't have to come to a well, sort of true understanding of the light, but use some models and predict outcome of different experiments. One model is this wave sort of function. Suppose these red lines here represent light finding some material system here, either at a point O or at a point P. O could be the origin in a coordinate system, and then each of the densities that scatter light will have a coordinate P. So, and suppose that one of all directions that light could be scattered at is for, if this is the incoming direction, then S means the outgoing, the diffracted direction. We assume that no energy is lost or gained. So this is a totally elastic scattering phenomenon. It has just to do with geometry of the different points. The difference, the radius vector between the 2 points P and O could just be a vector difference like that. And what should we use this figure for? Well, if the light is, if the wave is approaching the origin at O along the lower part here, or at the upper part at point P, there will be a length difference. The difference here from if this is a perpendicular projection, there is some longer distance of the red incoming ray to the point P than it is to point O. And there is also a longer distance of the outgoing green ray before it finds the same position in the S direction as a ray scattered at point O. So there will be a path length, extra path length here for the light to travel. And since light has a certain velocity, so one can calculate that if light should be modeled as a wave phenomenon, then this wave will sort of evolve, or the phase of the wave, the mathematical phase, we can see a wave as a, say, a sinus curve or something like that. The blue and red curve here, they are exactly the same function. They just shifted a little bit in phase. And suppose that the blue one is the correct one, then if the particle arrives a little bit earlier, then it would be like the red one here. The difference here is either spatial difference in geometry, or it could also be looked at as a time difference. This difference, the delta L, the difference in length, one can model it as the projection of the radius vector, this black line, times on the incoming wave vector, and the outgoing wave vector, whether it should be a minus or plus, or well, it should be at least the difference here. Why don't you add a plus here? That is probably related to the actual phenomenon here, that in the scattering event there will be a phase shift. So I think that is the reason why one usually have a minus sign here. But from a geometrical point of view, it's easy to define that the distance here is actually the difference between the distance here is nothing, and the distance here is quite long. And the phase difference will be how to phase of how many wavelengths is could be present on this extra distance. So divide this extra length by the wavelengths, and there you have the phase difference, at least in units. Multiply by 2 pi, and then you get the phase in radian measure. This is very popular. I'm not very good at drawing, I realize, because this should be this small vector S should be dividing this angle directly. So if this is a scattering, some object that scatters, and you have the incoming wave vector S0, we can normalize it to the wavelengths and then divide it by the wavelength. So this is a unit vector divided with the length 1 upon lambda. So the basic trees in between the incoming and outgoing vector small s is called the scattering vector. The symbols here are sometimes different in different books. S0 and outgoing S could be termed K0 and K. And perhaps the scattering vector is used to capital S, but I mean, from the scattering vector is anyway the basic trees between the incoming and outgoing vector. So from geometry, this is the scattering. If the whole deviation is 2 theta, then and if this is a unit vector, then one can maybe define some kind of planes here. Just purely hypothetical planes. They are similar to the planes in what is known as the Bragg equation, but they don't represent anything but mathematical idealization of a crystal's structure. There is some kind of arrangement that of atoms that let us define a repetition distance, for example. But staying with this scattering vector, this S half, and the unit here, and with the scale factor 1 upon lambda and the theta, this is approximately I think this is the something very, very similar to what is known as Bragg's law. 1 upon S is the distance, or 2 upon S. No, sorry, S half is the distance between the planes here. But if you interpret 1 upon S as the some kind of distance in real space, S is a wave vector, so that is not in real space, but in reciprocal space. So 1 upon it will be a real quantity. The phase difference was this 2 pi times the length difference, or expressed like that. Or one can also see it as the r dot s, the scattering vector. So this will be a very, very common expression that we will see. Whether it is minus or plus is of less importance. It's partly dependent on which direction we define as the positive direction. So going to scattering from very many points, it's easier to go over to some kind of exponential representation. Previously, this the scattering from one point, which is what we in principle model with this figure here. If we say that the amplitude of in any scattering vector direction is some kind of constant times e to the 2 pi I rs, This is a strange expression, but it is actually a very compact way of writing sinus and cosines. Here we have a sinus, for example, but I mean, in principle, one trigonometric function, sinus or cosine, is essentially they are more or less equivalent. So the e to the 2 pi I, I can make a whiteboard here. Do you see my pen line over the whiteboard?
Yep.
No?
Yes.
So the e to the something I alpha in principle could be, this is the Euler formula, one of them, but this is the only Euler I think that we will mostly use, at least. Instead of dealing with a cosine function and sine function, is very convenient to use an exponential, complex exponential in a way, but that is perhaps less of a problem. As soon as you get used to it, if you are already used, then it's no problem. You can draw it and illustrate it in a complex plane diagram. I'm not sure what it calls, an Argand diagram maybe. So if you have if this is the vector and this is the angle alpha, so the projection on the real axis is cosine alpha, if the vector is a unit vector at least, and the projection on the imaginary axis is sinus alpha. And to indicate that it is along the imaginary axis, we put the imaginary unit here. Imaginary units could be hard to understand what they are, but well, square of them is a real number. And if you have, I mean, it's just one complex number. If you have a calculator or computer program with the operations defined in complex space, then this is just a number as other numbers. Real numbers are also quite strange. You will get used to Thomson. Where did we go? Here. To complex numbers, at least if you try to check these formulas. Well, this is a scattering from one point. Or if you have many points, then it's just the sum of the the individual points. What defines the point in real space is r, the radius vector from the origin, and the direction in reciprocal space is the s here, is the scattering vector. When s goes varies between 0, length of s varies between 0, but the vector has a direction also. A 0 vector has perhaps no direction, but any other vector with a length bigger than 0 has a direction also. So the r dot s will, since this is a real space quantity and s is a reciprocal space quantity, this will be a number, just a real number. A real number times the imaginary unit and e to the I, this number, and multiplied by 2 pi. 2 pi is just because we want, this is, both of them are normalized. The quantity here should be normalized. If we add contribution from many points, it's just to sum over all points. So it's nothing strange about, it's nothing strange about that. Since A naught, the constant, the incoming amplitude, so to say, is a constant, then we can move it outside. We can't measure the amplitude, but we can measure the intensity of a scattered ray. In most directions, there won't be any scattering because there will be destructive interference in most directions. But in some directions, there will be scattered intensity, and then it's just to put a detector there and measure the intensity in a diffraction pattern. And this is what everything aims at, measuring intensities and trying to find the coordinates of the structure where the atoms are. So, but what information do these intensities contain? The intensity is defined as the amplitude square, or possibly the amplitude times the complex conjugate of the amplitude. Complex conjugates. And that is, now let's see, so if we have this complex plane with the real axis and the imaginary axis, and if you have a vector here, if this is u, then the complex conjugate denoted by this little star, for example, or there are probably different versions of what's it called, nomenclature, and that one can denote a complex conjugate. But if you take now u times the complex conjugate, then we will get something, this part and that part. I mean, the length of it corresponds to addition of the vectors. So we will have a result along the real space axis. So this is clearly a real quantity, which is good because the scattered intensity must really be a real quantity. Since each of the amplitudes in a direction s and the amplitude conjugate of s could be termed as a sum over all of the different positions, j. J goes from, say, 1 to number of objects that scattered in the radiation. And if we do express these double sum here, the constant could be multiplied outside, and the rest of it is just e to the 2 pi I. Rs, Rjs, and Rks. J and k are different indices. J runs from 1 to number of objects, and k runs also from 1 to number of objects. But not necessarily, this will be you can visualize it by a square matrix or something like that. So except when j and k are equal, then this difference will be exactly 0. But in every other respect, there will be some kind of value here, dot product with scattering vector. So do we actually find some information here? Yeah, we do. The intensities they're not dependent on the atomic coordinates directly, but they are, on the other hand, dependent on the interatomic distances, the difference between different atoms or different scattering objects. So that is not necessarily what we want, but from the intensities, one can in principle deduce the set of interatomic distances, which is a basis for heavy atom methods and such things, Patterson methods. We will be back to that. We want the atomic positions, but they are not directly, at least, possible to find from the intensities. But it's better than nothing. If the intensity is this expression, double sum over all objects that are scattering the intensity, the radiation, e to the 2 pi I, if you use this Euler formula, e to the 2 pi I rj minus rk, there will always be, then it will be a cosine of this one plus a sine of I sine of the scattering argument here. But since j and k are indices that run from 1 to number of objects, each one of them, there will always be a distance between atom j to atom k, and also a distance between atom k and atom j, which is exactly the same, but with opposite sign. This means that all of the imaginary terms, the sinus terms, they will cancel from this double sum. So the rest, what we are left with, is only a real, the real part of this Euler formula, the cosine terms here. And suppose you have a square matrix. This is 1 to number of objects. Say that j is moving there, and here is k from 1 to number of objects, a lot of different cells, trillions of cells in a reasonable crystal. But some of the cells will be along this diagonal, and the distance here of rj minus rk will be exactly 0. And the rest of them, they won't be 0, not necessarily, at least. They could be 0, but not by sort of geometrical symmetry arguments. But what does it mean? We can divide this sum over all j and k into the main diagonal. It's only the number of objects plus the rest, not including the main diagonal where j and k are unequal. This formula is perhaps a bit incomplete. But what does it mean? It means that the intensity is dependent. You will never have 0 intensity of a reflection, but you will have an intensity related to the number of atoms. On the other hand, this is linear in the number of atoms. The interference term here is quadratic because it's a double sum. It would be something like proportional to n square. So from a practical point of view, if you have say a zero scattering silicon wafer on the powder diffractometer, you will have a background, a small background in principle, but maybe not in practice detectable unless you go to some synchrotron device or free electron laser or any of those very, very intense X-ray sources. Then you will actually see this inherent scattering due to the fact that there is matter. This is not interference between, it's just scattering due to the fact that there are atoms. Usually in all practical cases, the interference term here is nearly infinite, if I may say so. I hope there are no mathematicians listening. But it's nearly infinite number of times bigger than this self-scattering. But in some cases, it could be in principle of interest to look at it. So instead of having, this is scattering objects where we have positions j and k, instead of denoted by this upper part here, instead of that, and this is one atom, this is several atoms, and instead of having certain objects, we could have a density distribution illustrated by the function here. And this is, for example, electron density distribution in atoms. So an atom could be, a density distribution could be viewed as a, not as a dot, and maybe as a collection of dots or a dotted environment around some atomic position, hypothetical position, where the dots are having a higher density close to the atom and a smaller density more far away from the atom. So what you will find is essentially either a dot, then it scatters, then the radiation scatters from there. And if that happen to find here, then it's just continuous. This is just useful for describing a scattering from one dot, or if you have several dots like that, then you will have a scattering from each one of them. Or if we make some kind of, if we have free coordinate distances here and some density, so you could have a small density and then larger density, and then this electron density will scatter a lot at this position, less here, and hardly anything when the atom is not present anymore. Or vacuum do not scatter, not at least in this classical theory. So this, how does it look like? Something like this for normal atoms. The e to the 2 pi I rs, rs could be viewed as something like sinus or cosine. And around 0, the scattering direction 0, it should scatter a lot. So it makes sense to look at the sinus, the sinus scattering direction upon lambda, and different atoms scatter differently. Here they are normalized so that the forward scattering should be 0 here, is equal to the atomic number. So carbon atom scatters with 6 units and oxygen with 8 units, oxygen 2- with 10 units, etc. And then the scattering falls off. And we call this scattering from one atom the atomic form factor. Why a form factor? Well, all of this is an atomic form factor integrated over the whole volume of the density distribution. Well, atoms, they are composed of some kind of density distributions, approximately spherical, and the incident beam, the electric field in the incident beam sets this. One could model it at least by the incident beam setting this electron density distribution into some kind of forced oscillation or vibration, or oscillation is perhaps a better word. And when it relaxes in some direction, it will emit X-rays. In most, in any direction, there is no reason why it shouldn't be a spherical wave. If the scattering is not totally elastic, elastic scattering means no energy transfer is, no energy is lost or gained from, for example, if the atom is moving, or if there is an atom initially at rest, if the atom starts to move, if we induce geometrical changes, vibrations, for example, in a molecule, then we lose energy from the incoming energy, incoming beam, and energy is constant. It must be constant. So then the outgoing beam here will be slightly different. And you can construct some kind of energy diagram if the incoming X-ray photon has some energy and some certain lambda. Then if for example, an electron is emitted from the atom, recoil electron, it represents some energy, or it could also be that the atom is just moving away. Then the scattered radiation will have a different wavelength. Less energy means a bigger lambda. The energy, some energy is lost in inelastic scattering. This could be used actually to if there are vibrations present in a molecule, then the X-rays, they will hit this molecule and the objects in the molecule, and lose or possibly even gain energy. But well, Compton scattering means losing energy, or that the energy is not constant. That is actually, I think, the correct way of viewing it. So that could actually be used to study vibrations and such things. The only problem is that the energy range of vibrations in most molecules, say it could be kilojoules per mole, maybe, the energy of the incoming ray here could be thousands of kilojoules or megajoules per mole. So the energy of X-rays is usually very, very large compared to the energies that occur in vibrating molecules and such things. So X-rays are hardly used to measure vibrations in solid materials. On the other hand, we will hear later in the course about neutron scattering. Neutrons could also be viewed as sort of radiation, and the energies of those particles are approximately equal to the energies of, or in the same range at least, as the energies of vibration states in solid materials. So with neutron radiation scattering, you can actually measure vibrational movements, and there are like infrared spectroscopy approximately, but a much more expensive machine. Yeah, this scattering from an array of atoms, this is close to a crystal. If each of the atoms could be described by a normalized atomic form factor, we can divide this, say this expression we indicated by f of s. It's not on bold S here, but it's just the since f is spherically symmetrical, we only need to know the magnitude of S. But if there are a lot of different atoms separated by some distance, for example, bold A, if in a sort of unit cell type with the unit distance A, then in principle it's just to use the same expression to, instead of as we previously did, where did we do it? Here, to sum over all the points to get a density distribution, or we could make this integration over a lot of different parts of real space. But that would be a bit cumbersome, so it's easier to split it up, this integral, in each atom, and then instead sum over the different atoms. And then one can say that the R here is the distance between each of the atoms within the atoms, and the A, this A here should, well, if we have an atom at the origin, then the interatomic distance would be only A. But summing over several different unit cells separated by some distance is approximately the same expression as before. But this sum runs over the different unit cells, or one could say that it is splitted between the different unit cells and each content of the unit cell that is they are similar to each other. So this is, we call the structure factor compared to the atomic form factor. This is a crystal structure form factor, one can say. And for short, it's a structure factor. Summing over a lot of different unit cell with n different unit cells in principle could also be expressed like something like that. And if we draw a graphical view of that, we will get here. This was a position times the scattering vector raised to the power of n number of unit cells. And I don't, here is 10 unit cells. And you see that the scattered intensity is hardly present except when this A dot S is a unit, an integer. And then it goes down and then it increases again, another integer. Then one can say that summing over a lot of different unit cells, this will only do a constructive interference effect when A dot S is an integer number of 2 pi. So the A dot S, if that is an integer, H should be interpreted as an integer here. And since real crystals, they are periodic in 3 different directions, A, B, C. So one can say that this sort of scattering event or the this condition should be fulfilled in all 3 directions if we should have a reflection. If the intensity in that direction, in the direction S, should be scattered, then we have a simple expression for doing checking that is taking the A dot S, if that is an integer, if the B dot S is also an integer, and C dot S is also an integer, then we have a reflection. This is called the LAUE equations for just in a way enumerating the reflections in a scattering experiment. Usually we call the reflection HKL. We speak about the 1, 2, 3 reflections, for example. And that means that the repetition along A and this scattering D direction is an integer. In between the reflections, there are no scattered radiation. At least, well, with 10 atoms, you can see some ripples here. But if you would draw this figure with 100 atoms, this is simple to do because you can just compute this sum. You can skip these scale factors here. It is just this sum that is of interest. Then with 100 atoms, then it's more or less flat here. And also the intensity is, the width of the intensity is smaller and smaller. What happened? My hello, I got lost on my electricity on the computer, but we can take a break until 11 o'clock or something like that.
Yes.
Sounds good.
Sounds okay.
Or maybe 11:05.
Okay.